Okay, for part C today, we'll start with section 7.4, which is about formal charges and resonance. Formal charges are something that you can utilize to decide between rival, basically rival Lewis structures when more than one plausible Lewis structure can be drawn for a given molecule. Sometimes that occurs with like some of the examples we saw where we had, for example, SO2. Sulfur dioxide has a double bond between sulfur and one of the oxygens and a single bond with the other oxygen. You could have drawn, like I did, the double bond between the sulfur and the oxygen on the left, but it would be just as correct to draw that double bond between the sulfur and the oxygen on the right. Those are two different ways of drawing the picture or drawing the subject, and maybe one of them is better than the other. So how would you decide? Well, formal charges might be a way to do that. There are some other examples where plausible Lewis structures could differ even more, like maybe one Lewis structure has a double bond in it and the other doesn't have any double bonds in it. That's a pretty big difference. So, and they might look equally plausible, but formal charges gives you a way of deciding which one is better. The formal charge is really just a hypothetical charge that an atom would have on it if all of the electrons in all of the bonds in the molecule were distributed evenly. And it's a hypothetical charge, not a real one, because of course we know in real molecules, the electrons and bonds are usually not distributed evenly because most bonds involve atoms of elements that have different electronegativities. And the one that's more electronegative will pull the electrons closer, and the one that's less electronegative will have the electrons pulled away from it. And so one end of the bond tends to be more negative than the other. That's basically true whenever the atoms are of different elements. But formal charges are kind of like a bookkeeping method that we can use to decide which structure is best based on these hypothetical theoretical charges. The formal charge can be calculated for any single atom in any Lewis structure. And for each atom in the Lewis structure, its formal charge would be the number of valence electrons, that is its normal number of valence electrons, according to the periodic table, minus all of the lone pair electrons on that atom, minus half of the bonding electrons around that atom. So we're kind of making an assumption here that when electrons share, or when atoms share electrons, one of the electrons originally belonged to one atom and one of the electrons originally belonged to the other atom. So we're kind of recreating that situation by only subtracting half of the bonding electrons on the atom. The one rule is that for any structure to be valid, the total of all of the formal charges for all of the atoms in a structure have to be equal to the overall charge on the structure. So if we're talking about a molecule which has zero charge overall, then the total of all of the formal charges on all of the atoms in the structure better add up to zero. And anytime it doesn't add up to zero, that structure is wrong. If you're working with an ion, then the total of all of the formal charges on all of the atoms in the ion have to equal the charge on the ion. So like with the nitrate ion, all of the formal charges on all of the atoms in the nitrate ion have to add up to -1 because that's the charge on the ion. And if they don't, then something is wrong. The best structure will generally be the structure that has as many formal charges of 0 as possible. And if you can't get them all to be 0, like in the case of an ion, obviously if they have to add up to -1, like on the nitrate ion, then they can't all be 0. Then you at least want to have as many of them as close to 0 as possible. Any negative formal charges should be on the most electronegative atoms present. not on the less electronegative atom, because electronegative atoms want electrons more than other atoms do, and therefore they're more likely to have a negative charge on them because they're going to grab the electrons. And any adjacent formal charges, that is, formal charges on atoms that are right next to each other, should be either 0 or of opposite signs. So you're not going to find like two formal charges of +1 on two atoms that are right next to each other. Could be +1 and -1, or it could be 0 and 0, but you won't find like +1 and +1 or -1 and -1. And so one way we could look at it, and I'm going to go back and assign the formal charges for the structures that we did in, actually, I'll do that now. For the structures we did in when we were doing Lewis structures, we had NO3 minus, which we saw had a structure of this. Okay, and the formal charge, let's start with the nitrogen, would be the normal number of valence electrons for nitrogen, which is 5, minus all of the lone pair electrons on the nitrogen. Well, nitrogen doesn't have any lone pair electrons here, so that's -0. Minus half of the bonding pair electrons around the nitrogen. Remember, each bond has 2 electrons in it. So there's 2, 4, 6, 8 electrons in bonds around the nitrogen. So 5 minus 0 minus 1/2 of 8. In other words, 5 minus 4 is +1. The formal charge on the single bonded oxygens. Now, if you look at the structure, both of these single bonded oxygens are exactly the same. They're single bonded to the nitrogen, and they each have 3 lone pairs and 1 bonding pair. So what I say about, I'm only going to do this once for the single bonded oxygen, and it'll count for both of them. So for the single bonded oxygen, oxygen normally has 6 valence electrons. That will, from that, we will subtract 1, 2, 3, 4, 5, 6 lone pair electrons. And from that, we will subtract half of the 2 bonding electrons. And that's -1. The other single bonded oxygen is exactly the same, so that is also -1. And now the double bonded oxygen is going to be 6, because that's the normal number of valence electrons for oxygen, minus 1, 2, 3, 4 lone pair electrons, minus 1/2 of 2 bonds means 4 electrons, so that's 1/2 of 4. 6 minus 4 minus 2 is 0. And when you add all of these up, +1, -1, -1, and 0, the overall charge is -1. And so this is a good structure for that. We've got relatively small charges. They add up to -1 like they should. And we don't have the 2 -1 charges. They're not right next to each other. You have to go through the nitrogen to get to the other oxygen. So you've got -1, +1, -1. So we have oppositely charged formal charges that are right next to each other. So that works out, and there are your formal charges. And that means that that's probably correct as a Lewis structure. For SO2, we ended up with oxygen double bonded to sulfur, single bonded to the other oxygen. We ended up with that as the Lewis structure. And the formal charge on the sulfur will end up being the normal number of valence electrons for sulfur, which is 6, minus the lone pair electrons on the sulfur. Oh, sorry, there was a lone pair on the sulfur, wasn't there? Minus the lone pair electrons on the sulfur, which is 2, minus 1/2 of the bonding electrons on the sulfur. 3 bonds means 6 electrons. So 6 minus 2 minus 3 would be +1. The formal charge for the single bonded oxygen is going to be the number of normal valence electrons for oxygen, again, which is 6, minus the bonding pair electrons on the single bonded oxygen, which is 6, 1, 2, 3, 4, 5, 6, minus half of the bonding electrons. There's one bond, that means 2 electrons. 6 minus 6 minus 1 is -1. Okay, for the double bonded oxygen, the one on the left as I drew it here, that's going to be 6 because that's the normal number of valence electrons for oxygen, minus the 4 lone pair electrons on the double bonded oxygen, minus 1/2. Now 2 bonds means 4 electrons, so 1/2 of 4, or yeah, 1/2 of 4. 6 minus 4 minus 2 is 0. So the total of the formal charges is 0. The negative charge was on an oxygen, which is the more electronegative element present. Oh, and by the way, that was true for the nitrate ion also. Negative ones were on oxygens, which is more electronegative than nitrogen. So that was a good sign. And so that means that this is a good Lewis structure. Okay, and then XEF4, we've got the Lewis structure XEF, and then the lone pairs. Okay, so the formal charge on the xenon is going to be 8, because that's the normal number of valence electrons for xenon. It's one of the noble gases, minus the number of lone pair electrons on the xenon, which is 4, minus 1/2 of the bonding electrons on the xenon, which would be 2, 4, 6, 8. 8 minus 4 is 0. All of the fluorines on the xenon are exactly the same as each other. They're all single bonded to the xenon. So I'm only going to do one of the fluorines, and that, what is true of one fluorine will be true of all of them. So fluorine normally has 7 valence electrons. We subtract 6 because it's got 6 lone pair electrons around it, and then 1/2 of the 2 electrons in the single bond to the xenon. 7 minus 6 minus 1 is 0. So in this structure, all of the atoms have 0 formal charges, which is really good. And the overall charge should be 0, and the zeros add up to 0. So that's a good sign. And then aluminum chloride, we saw that aluminum chloride is just aluminum surrounded by 3 chlorines, all with octets. The formal charge on the aluminum is going to be normal number of valence electrons for aluminum is 3 because it's in group 3A, minus lone pair electrons on the aluminum, which is 0, minus 1/2 of the bonding electrons around the aluminum. 3 bonds means 6 electrons, so that's minus 1/2 of 6. 3 minus 0 minus 3 is 0. The chlorines are all the same as in the case with the fluorines in XEF4. So I'm only going to do one of the chlorines, and this will represent all of them. Chlorine normally has 7 valence electrons. Each chlorine here has 6 lone pair electrons. And a single bond means 2 electrons, so you subtract 1/2 of 2. 7 minus 6 minus 1 is also 0. So again, all of the atoms in this Lewis structure have 0 formal charges. That's a good sign. They add up to 0, which is the overall charge on aluminum chloride, because that's a molecule, not an ion. And that's a good sign. And so that is the correct Lewis structure for aluminum chloride. In the examples that I'll pick up with where we left off, we were going to actually look at possible Lewis structures that actually are significantly different from each other and are all seemingly plausible because they all achieve the result of having octets around all of the atoms. And so if we're looking at the structure of silicon dioxide, or SiO2, the question is, which of these Lewis structures is the best? We can look at the first one where silicon is in the middle. Now, normally you would expect silicon to be in the middle because there's only one of them in the formula, and because silicon is less electronegative than oxygen. But there are some exceptions to that idea. There are compounds, for example, that involve nitrogen and oxygen where oxygen ends up in the middle, even though there's more than one oxygen. So, and formal charges can actually help you determine that. That the structure that you would be tempted to draw with nitrogen in the middle is actually not the best structure. Formal charges are a way to tell that. With SiO2, we can look at silicon in the middle with double bonds to both oxygens. Now, right off the bat, I would say that this structure makes the most sense because, for one thing, you got a silicon in the middle and an oxygen on either side, and both of those oxygens are atoms of the same element. So they have the same level of attraction for electrons, and there's no reason to think that they would come out different from each other in the atom unless it's really necessary for them to come out different from each other, like it was in SO2. There's no way to make SO2 work unless one of the oxygens has a single bond and the other has a double bond. But in this case, we know that there are 4 bonds on the silicon, and it makes perfect sense that 2 of them would be to the oxygen on the left and 2 of them would be to the oxygen on the right, because they're both oxygens. Why would they be different? As opposed to the structure below it, where one oxygen has a single bond and the other has a triple bond. Why would it do that? But anyway, we can prove it with formal charges. The formal charge on the silicon in this first structure would be 4, because that's the normal number of valence electrons for silicon, minus the 0 lone pair electrons on the silicon, minus 1/2 of the 8 bonding electrons on the silicon. 4 bonds means 8 electrons. So 4 minus 4 is 0. The formal charge on either of the oxygens, because they're both the same, so I'm only going to do one of them here. The formal charge on the oxygens would be 6 minus the 4 lone pair electrons on the oxygen, minus 1/2 of the 4 bonding electrons. Remember, 2 bonds means 4 electrons. Well, 6 minus 4 minus 2 is 0. So everything in this structure has 0 formal charge. It adds up to 0, which is the charge on SiO2 because it's a molecule, not an ion. And so that is a really good Lewis structure. But we might as well look at the other 2 because maybe somehow one of the others ends up being even better. Okay, the one with a single bond and a triple bond. For one thing, as I said a little while ago, oxygen has 6 valence electrons of its own, so it normally only wants to form 2 bonds because it needs 2 electrons to get to an octet. Going from 6 to 8 electrons, it needs 2 more, so it would tend to form 2 bonds. Could form 2 single bonds or 1 double bond, but it really doesn't want to form a triple bond. So as we look at this, we can look at the silicon, and again, it's 4 minus 0 minus 1/2 of 8, because the silicon still has an octet of bonding electrons around it and no lone pairs, just like in the first example. So like in the first example, the formal charge on the silicon ends up being 0. The formal charge on the triple bonded oxygen would be 6 minus the two lone pair electrons on the triple bonded oxygen, minus 1/2 of the 6 bonding electrons on the triple bonded oxygen. 3 bonds means 6 electrons. So 6 minus 2 minus 3 is +1. And the formal charge on the single bonded oxygen is going to be 6 minus the 6 lone pair electrons on that oxygen, minus 1/2 of the 2 bonding electrons involved in that single bond, and that means -1. So the total here is still 0 plus 1 minus 1. The total still comes out to 0, but you've got a +1 and a -1 here, whereas in the first example, we had all zeros. So the first example is definitely better than the second. The third example, with an oxygen in the center, gets really weird. And, it seems weird, and it is weird. The formal charge on the silicon this time, because silicon's not in the center anymore, the formal charge on the silicon will be 4, because that's its normal number of valence electrons, minus the 4 bonding electrons, minus 1/2 of the 4, minus all 4 of the lone pair electrons on the silicon, minus 1/2 of the bonding electrons. Silicon here has 2 bonds, which means 4 electrons. So 4 minus 1/2 of 4, that's 4 minus 2. That gives you a -2 formal charge on the silicon, which is the least electronegative element present. That's a really bad sign. For the formal charge on the oxygen in the middle, that is the oxygen with the double bonds on both sides, that would be 6 minus 0 lone pair electrons, minus 1/2 of the 8 bonding electrons around it, which would give you a formal charge of +2. You've got a positive charge on the most electronegative element present. That's a bad sign. The formal charge on the oxygen on the end, the one that only has one double bond, would be 6 minus the 4 lone pair electrons on it, minus 1/2 of the 4 bonding electrons. 6 minus 4 minus 2 is 0. Yeah, so you've got +2 and -2 in this structure. Right away, anytime you have +2 and -2, that's usually a bad sign in and of itself. But the fact that you've got a negative charge on the less electronegative element and a positive charge on the more electronegative element, that's a really bad sign. So this is absolutely not the structure for SiO2. The second one is not great, but not terrible either. The first one, though, is really, really good. So that is by far the most likely structure. Let's see, the next topic here that we come to is resonance. I'll just go into this in a little detail because we're getting close to the end of this segment, so I'll count this as the official end. But resonance happens sometimes in molecules where you have a central atom that's bonded to outer atoms that are the same as each other. And sometimes the electrons in the bonds between the central atom and the outer atom are not as fixed in place as the normal Lewis structure would imply. Sometimes those electrons can actually spread out over more than one bond, or between more than 2 atoms. And that ends up being what's known as resonance. The electrons kind of spread out. That has the effect of stabilizing the molecule. But it also gives us weird stuff like bonds that are halfway between single bonds and double bonds. There's like 1.5 bonds, which is kind of a strange concept. But that's because of the delocalization of the electrons, as it's called. So anyway, we'll pick up with resonance next time. And for now, I'll see you later.